Welcome to the deep dive. For anyone building software today, there's this recurring nightmare, right? Predicting exactly how much infrastructure you'll need for your next big launch.
Okay, definitely.
Maybe you're spending endless hours patching operating systems, battling security vulnerabilities, or simply watching expensive servers sit idle during off-peak hours. Just slowly but surely burning through your budget. It's a universal developer and business headache, isn't it?
It absolutely is. It's that constant worry.
Well, what if I told you there's a transformative solution where your code just runs like magic? No servers to provision, no OS to patch, no traffic spikes to predict with a crystal ball. Just your application logic effortlessly handling demand.
It truly sounds like a developer's utopia, doesn't it?
Right.
And the fascinating thing is, it's not some distant dream. That ideal is actually a core promise of what we're diving into today.
That's precisely right. Today, our deep dive takes us straight into the heart of AWS Lambda. Our mission is to fundamentally grasp how Lambda manages to, liberate you from those infrastructure management burdens, allowing you to pour all your creative energy and problem-solving prowess directly into your code.
Yeah, focusing on what actually matters for the business or the user.
Exactly. We'll unpack precisely what Lambda is, explore the scenarios where it becomes, the absolute best tool in your arsenal. We'll pull back the curtain on how it orchestrates its magic behind the scenes, delve into some of its most compelling advanced features, and even tackle a really crucial practical consideration that can save you, honestly, significant technical snags down the line.
And it's important to stress, this deep dive isn't just for the seasoned cloud architects or the hardcore tech gurus, right?
Not all.
This is really about comprehending a foundational shift in how modern applications are constructed. It's about recognizing a paradigm that profoundly impacts development speed, enables truly unprecedented scalability, and can dramatically reshape your cost structure. Ultimately, it's about understanding what it means to innovate at the speed of thought in this cloud era.
All right, let's truly unpack this. Let's get into it. So let's kick things off by grappling with the core concept. You consistently hear the term serverless whenever AWS Lambda comes up, but for our listeners, what does serverless actually signify? Because, let's be honest, the servers themselves haven't physically vanished, have they? They must be somewhere.
That's such a critical distinction to make right at the start. It's probably one of the most common misconceptions out there. Serverless, in the context of AWS Lambda, doesn't imply the literal absence of servers. Not at all. Instead, it means that you, the developer, the operations team, the business owner, you are entirely abstracted from the responsibility of provisioning, managing, or even thinking about those underlying servers. The profound concept here is that AWS Lambda runs your code on a high-availability compute infrastructure, and it's AWS, not you, that manages all the computing resources required to execute your code.
Okay, so when you say all the computing resources, that sounds like a colossal amount of operational overhead that Lambda just absorbs. What exactly does that cover from my perspective as someone using it?
It truly is a colossal burden lifted right off your plate. This includes everything from the ongoing server and operating system maintenance. So really, no more late-night patching of vulnerabilities or manually applying updates to dynamic capacity provisioning, which means you never have to guess or manually allocate how much compute power you'll need for peak loads. Lambda also handles automatic scaling, seamlessly adjusting resources up or down in real time based purely on demand, ensuring your application always performs optimally.
Always?
Well, within configured limits, but yes, the goal is optimal performance. And crucially, it even manages the logging and monitoring aspects, providing you with built-in visibility into your code's execution without you having to configure complex logging infrastructure yourself.
That sounds incredibly liberating. I mean, thinking about the traditional approach, just imagine you're running a massively popular e-commerce site. As Black Friday approaches, you're not just hoping for the best, you're manually spinning up dozens, maybe even hundreds of additional servers just to brace for that expected traffic surge.
Right, the pre-provisioning nightmare.
And then, once the holiday rush subsides, those servers just sit there, often mostly idle, still costing you money, until the next peak. That's a direct capital expenditure that often turns into, wasted operational cost.
Precisely. And the truly profound impact of Lambda is that it liberates you from that entire cycle of over-provisioning and then subsequent underutilization.
Yeah.
You're no longer spending valuable developer and operational team time on infrastructure upkeep and capacity planning.
Yeah, that time is expensive.
Incredibly. Instead, those precious resources can be fully redirected toward actual product innovation, building new features, enhancing the user experience. This fundamentally alters your cost structure too. You're shifting from a CapEx-heavy infrastructure model where you buy servers up front regardless of usage, to an OpEx-driven consumption model where you literally pay only for the compute time your code actually uses, often down to the millisecond.
Down to the millisecond.
Yeah, it's incredibly granular. This really democratizes innovation, allowing smaller teams or startups to achieve massive scale without needing a huge dedicated operations team, and to experiment and pivot with minimal upfront investment.
That's a significant shift. Okay, here's where it gets really interesting for me, the clear delineation of roles. If Lambda takes on all that immense infrastructure management, what are you, the developer, actually responsible for? What's left on your plate?
With AWS Lambda, your responsibility becomes singularly laser-focused. Your code.
Just the code.
That's basically it. You write your application logic, and Lambda then takes on the immense task of managing the entire compute fleet that executes it. And it's a highly optimized global fleet that provides a perfectly balanced allocation of memory, CPU, network bandwidth, and other essential resources, all specifically tailored to run your particular code efficiently and at scale. It allows you to think purely about business logic, not server racks or operating systems.
Okay, so this clearly implies a fundamental trade-off, doesn't it? If Lambda manages everything, I can't just SSH into a server to inspect your runtime issue or install some very specific kernel module that maybe a highly specialized legacy application might require. For developers accustomed to the traditional server model, how significant a hurdle is this perceived lack of control? When does it become a real blocker for adopting Lambda?
That's a really insightful question, and it definitely highlights a critical characteristic of the managed service. You are absolutely correct. You cannot log in to the underlying compute instances, nor can you customize the operating system on the provided runtimes in the standard sense. For developers who are used to having full root access and deep visibility into the OS, this can indeed feel restrictive at first. However, this apparent lack of control is fundamental to the serverless promise. It's actually how Lambda achieves massive scalability, high reliability, and unparalleled operational simplicity for you.
Ah, okay, so it's a feature, not a bug.
Exactly. It's a deliberate design choice that trades that granular OS-level control for extreme agility, cost efficiency, and automated resilience. The hurdle becomes a blocker really only when your application has highly specific low-level OS dependencies that aren't compatible with Lambda's managed runtimes, or perhaps its container image support, which you can talk about later. Or maybe if your debugging strategy solely relies on SSHing into a live server.
Which hopefully isn't the only strategy anymore.
Hopefully not. For the vast, vast majority of modern cloud-native applications, the benefits of this abstraction far, far outweigh this trade-off.
And how do you even structure your code in this environment? Do you just upload one giant code base, or is there a more modular approach?
Not at all. It's very modular. Your application logic is organized into what are called Lambda functions. These functions are the basic, self-contained units for building any Lambda application. Think of them as individual, specialized pieces of logic. Each is designed to perform a specific, discrete task.
Okay, like little microservices almost?
Sort of, yeah, that's one way to think about them. The Lambda service then takes these functions and runs them only when needed, in response to some kind of event. And critically, it scales automatically to meet any surge in demand, from literally 0 to thousands of concurrent executions in moments.
I love a good analogy for something like this. So if your code is a function and it only runs when needed, is there an analogy that really helps solidify this on-demand nature for our listeners?
That's a great challenge. Okay, let's try this. Imagine you need a taxi to get across town.
Right.
You don't go out and buy a car, hire a full-time driver, and keep him on standby 24/7 just for your occasional trips. That would be incredibly inefficient and expensive, wouldn't it?
Totally impractical.
Exactly. Instead, you simply request a taxi when you need one. A taxi shows up, takes you where you need to go, and then it's gone, ready for the next passenger. Similarly, a Lambda function only executes when a passenger, which is an event, explicitly requests it.
Ah, the event is the passenger.
Okay. And if there's a sudden surge in demand, like hundreds of people simultaneously needing a taxi at rush hour, the service can instantly scale to dispatch hundreds of taxis, or in this case, hundreds of function invocations to handle that demand seamlessly. This on-demand, pay-per-use model is incredibly efficient, minimizing waste and maximizing responsiveness.
That taxi analogy truly paints a clear picture. Okay, so we understand what Lambda is and its fundamental operating model. But now for the big question for many of our listeners, When should I actually use this? What are the ideal scenarios where AWS Lambda truly shines, and perhaps where it becomes the obvious go-to solution?
Yeah, the when is key. What's truly fascinating here is that Lambda is uniquely suited for application scenarios that demand two critical and often kind of contrasting capabilities. First, rapid scaling up when demand surges unexpectedly. And second, the ability to scale completely down to zero when there's no demand at all.
Down to zero, that's the cost part.
Precisely. This is where its unparalleled cost efficiency comes into play, because you literally only pay for the compute time your code is actively using. There's no cost for idle servers, which is frankly a game changer for many business models.
That's a huge advantage, truly. So for our listeners who are now thinking, okay, I get it, but when does this truly become my go-to solution? What are some of those powerful real-world scenarios where Lambda fundamentally transforms how applications are built?
Okay, let's dive into some specific, powerful examples from the sources. We can definitely start with stream processing. This is a classic. When you combine Lambda with Amazon Kinesis, which is AWS's real-time data streaming service, it becomes an incredibly robust and scalable engine for processing real-time streaming data.
Okay, like what kind of data?
Well, we're talking about use cases like meticulously tracking every single user action on a large application as it happens, or processing transaction orders in milliseconds, or conducting detailed clickstream analysis to understand user behavior patterns instantly.
And it goes even further than that, right? I've seen it used for things like real-time data cleansing, filtering out noise from massive log streams, maybe on-the-fly data indexing for search capabilities.
Absolutely. Or even analyzing social media trends as they emerge, providing immediate insights. The beauty here is its ability to handle immense, often very spiky volumes of incoming data. The sources also highlight its critical utility for Internet of Things, or IoT, device data telemetry, essentially, collecting and processing data from millions, maybe even billions, of connected devices and sensors globally.
Wow, billions.
Potentially, yeah. Imagine a smart city infrastructure or a massive fleet of industrial sensors, all sending data constantly, or in bursts. Lambda's concurrent, event-driven model is uniquely suited for these bursty, high-volume data streams because it can instantly spin up thousands of instances to process events as they arrive, then scale right back down when the deluge subsides. Unlike traditional always-on consumers that might be over-provisioned or just get overwhelmed.
Right, they'd fall over.
Exactly. It's also vital for metering, which is crucial for modern usage-based billing systems across various industries. This just demonstrates Lambda's power for real-time data ingestion and transformation, which is absolutely critical for any modern analytics platform or responsive system.
Okay, so that covers real-time data ingestion really well. What about the classic use case, the backbone of almost everything on the internet? Web applications. Can Lambda truly power those effectively?
Most definitely. For web applications, you can combine Lambda with other foundational AWS services, like Amazon API Gateway for handling HTTP requests, and maybe Amazon S3 for hosting static content. With this combination, you can build incredibly powerful web applications that automatically scale both up and down and inherently run in a highly available configuration across multiple data centers, or availability zones as AWS calls them.
So built-in resilience.
Built-in resilience. This means your application is not only resilient to massive traffic fluctuations, but also inherently accessible and robust against regional outages. Think about an e-commerce platform that can handle Black Friday's millions of requests per minute without a single manual server adjustment. That's the power we're talking about. The application just scales seamlessly with demand.
Okay, but I imagine for complex web applications, managing all those interconnected Lambda functions and other services would require some serious orchestration and repeatable deployment. Are there tools that help manage that complexity? Because it sounds like it could get messy.
Yes, absolutely, and that's a very important point. This is where the concept of infrastructure as code, or IAC, which, essentially means defining your infrastructure like compute resources, network configurations, security policies all through code instead of manual clicks, really comes into play.
Treat infra like software.
Exactly. The sources highlight several IEC and orchestration tools that developers widely leverage. These include AWS CloudFormation, the AWS Cloud Development Kit, or CDK, or the AWS Serverless Application Model, IASAM. These tools help you define, version, and deploy your entire serverless application stack repeatably and reliably.
Okay.
And for orchestrating truly complex multi-step workflows, perhaps involving multiple functions and external services, maybe with error handling and retries, you can even use AWS step functions.
Yeah.
These tools enable you to treat your infrastructure like software, applying software development best practices like version control, testing, automated deployments, which is crucial for maintaining agility and reliability at scale.
That's a powerful picture of scalability and maintainability. What about mobile apps and Internet of Things devices that inherently need a robust and scalable backend? Is Lambda a good fit there too?
Oh, absolutely. For mobile and IoT backends, Lambda is often an ideal choice, streamlining the entire backend development process. You can build these backends by using Lambda in conjunction with Amazon API Gateway to handle all incoming API requests and manage authentication for your mobile or IoT devices.
Okay, so Lambda handles the logic, API Gateway handles the front door.
Pretty much. And for particularly easy integration with front ends like iOS, Android, web, and React Native applications, you can leverage AWS Amplify. It simplifies a lot of the client-side integration. This entire setup simplifies the back-end logic for modern distributed applications, whether they're serving a popular mobile app, collecting data from a network of IoT sensors, or integrating seamlessly with a complex third-party API. It allows your front-end developers to focus purely on the user experience, knowing the back-end will just scale automatically.
That's a remarkably broad scope. Now, something that almost every application deals with at some point is files. Uploading, downloading, processing. How does Lambda handle file processing efficiently?
This is a fantastic demonstration of Lambda's event-driven architecture in action. For file processing, you can configure Amazon Simple Storage Service, or Amazon S3, to directly trigger a Lambda function in real time immediately after a file upload or modification.
Wait, so if a user uploads a high-resolution image to my photo sharing application, Lambda can automatically resize it into multiple smaller versions for thumbnails or different display sizes,
Yeah.
all without any manual intervention from me, like instantly.
Exactly. Or consider processing a document as soon as it's uploaded for text extraction using something like Amazon TextExtract, or automatically converting large video files into different streaming formats the very moment they land in an S3 bucket. This means your back-end processes are initiated instantaneously and automatically, eliminating the need for constant polling or complicated scheduled jobs or any manual intervention. It's event-driven architecture at its finest, translating directly into faster user experiences and much more efficient workflows.
Moving beyond files, what about interacting with databases? Can Lambda play a significant role in database operations and integration? Seems like a common need.
Absolutely. For database operations and integration, Lambda can process database interactions in incredibly dynamic ways, both reactively and proactively. For instance, it can handle queue messages, say, from Amazon SQS for Amazon RDS operations. This allows you to process things like new user registrations or fulfill complex order submissions asynchronously, offloading work from your main application threads, which improves responsiveness.
Okay, so it can react to queues.
Right. And critically, it can also respond directly to changes in Amazon DynamoDB, which is AWS's highly scalable NoSQL database, using DynamoDB streams.
Ah, okay. What would that enable?
Well, this enables powerful use cases like real-time audit logging for every single data modification, or automated data replication across regions for disaster recovery, or triggering automated workflows based on specific data modifications. For example, sending a welcome email when a user's status changes in the database.
That's pretty powerful automation.
It truly extends the reach of serverless compute into critical data management tasks, enabling powerful automation and real-time responsiveness that would be far more complex and probably more fragile with traditional architectures.
So it's not just for real-time, high-traffic web scenarios then. Can it also handle more traditional routine tasks, things that might typically run on a scheduled cron job on some dedicated server humming away in a corner?
Yes, absolutely. That's another really common and valuable use case. For scheduled and periodic tasks, Lambda, integrated with Amazon Event Bridge rules, can execute time-based operations with incredible reliability and scalability.
Like cron jobs, but better.
Essentially, yeah. And think of these as supercharged, highly reliable versions of your old cron jobs running on a traditional server. You can use standard cron-like expressions, on the stuff or fixed-rate schedules to trigger functions for things like daily database cleanups, automatically archiving old data to cheaper storage tiers like S3 Glacier.
Oh, that's smart for cost saving.
Exactly.
Okay.
For generating weekly or monthly business reports or handling any other routine time-based business processes. This completely eliminates the need for dedicated servers just to run these periodic tasks, providing greater reliability, built-in logging, and seamless scalability without you having to manage operating systems or worry about server uptime for that cron box.
It really seems to cover a vast array of use cases, doesn't it? From the very immediate high-volume transactions to the very routine, scheduled administrative tasks. It's incredibly versatile.
It really is. The flexibility is one of its strongest points.
That's a pretty comprehensive list of applications. It really shows just how versatile Lambda is across different computing paradigms. But let's pull back the curtain a bit more now. How does it actually work internally? You've emphasized that it's event-driven, which sounds like a fundamental departure from traditional programming models that might be constantly running and waiting for requests.
It is indeed a fundamentally different programming paradigm, and really getting your head around this event-driven model is absolutely key to grasping Lambda's inner workings and leveraging its full potential. Because Lambda is a serverless event-driven compute service, it operates on a trigger and respond basis, rather than being an always-on, long-running process like a traditional web server.
Yeah.
This fundamentally changes how you design your applications, often moving towards highly decoupled, asynchronous architectures, less monolithic.
Okay, so what are the core components that make this trigger and respond model function? We've talked about Lambda functions being the building blocks, but what else is involved in making that happen?
Precisely. First, as we've established, you have your Lambda functions. These are, like we said, the basic building blocks where your actual code resides. They're self-contained and designed to perform a specific, usually single task.
Right. One function, one job, ideally.
Ideally, yeah, promotes good design. Second, and crucially, you have event sources and triggers. This is where the event-driven part truly comes alive. Various AWS services like S3, SQS, DynamoDB, API Gateway, EventBridge, many others, or even external applications act as event sources that publish events. These events then trigger your Lambda functions.
So the event source causes the trigger.
Exactly. When an event occurs, like a new file being uploaded to S3, a message arriving in an SQS queue, a change in a DynamoDB table, or an HTTP request coming through API Gateway, that event source notifies Lambda. Lambda then invokes your designated function, passing the event data to your function, typically in a standardized JSON format, for your code to process. This also includes a concept of event source mappings, which are specific configurations that define how Lambda consumes events from certain stream or queue-based services, handling things like batching multiple events together or managing retries if your function fails.
Okay, so extending our taxi analogy from earlier, the event is the passenger making a request, and the event source is like the taxi dispatch system sending the nearest cab. It's not constantly pulling, but rather reacting to a specific signal.
That's a perfect way to think about it. This trigger and respond model is absolutely fundamental to its efficiency. Your function isn't sitting idle, constantly waiting for a request, consuming resources, and racking up costs. It's only invoked when an event specifically triggers it, it processes that event, and then it effectively scales down, often to zero, when the processing is complete. This efficiency translates directly into cost savings and that inherent scalability we talked about.
Makes sense. And when it comes to security, always a top concern. How do you control what your Lambda functions can actually access? And conversely, what can interact with them? Because in the cloud, managing permissions is a massive critical concern.
It is critically important, yes. And thankfully, Lambda provides robust mechanisms for this. You control security and access through Lambda permissions. This involves two main powerful mechanisms, usually based on AWS Identity and Access Management, or IAM.
IAM.
First, use execution roles. These are essentially IAM roles that you attach to your Lambda function when you create or configure it. These roles define precisely what AWS services and resources your function itself is allowed to interact with. For example, giving a Lambda function permission to read from a specific S3 bucket, write logs to CloudWatch, or put items into a particular DynamoDB table.
So what the function can do.
Exactly. And second, you have resource policies. These are attached to the Lambda function itself and define what external entities or other AWS services are allowed to invoke or interact with your specific Lambda function's code.
Ah, so who can call the function?
Right. This granular control, controlling both what the function can do and who can call it, is absolutely crucial for securing your serverless applications. It allows you to strictly adhere to the principle of least privilege access.
Least privilege, always the goal.
Always. It means your functions only have the permissions they strictly need to perform their designated task and nothing more. This significantly reduces the potential blast radius if something goes wrong or if a function were somehow compromised.
That makes perfect sense. It's about giving your functions just enough power to do their job and no more, significantly reducing the attack surface. And how about the actual environment where your code runs? Is it like a bare bones Linux container or something more specialized that ensures consistency every time?
It's more specialized. Lambda runs your code within specific, isolated execution environments. AWS provides language-specific runtimes for popular languages like Node.js, Python, Java, C#, Go, Ruby, and others. These runtimes are pre-configured and optimized by AWS to execute your code efficiently within the Lambda environment.
So they handle the language setup.
They do. These runtimes are then packaged within these execution environments. But it's not just the runtime. These environments also include other important components like layers and extensions, which we should definitely delve into in a moment as they add significant capability.
Okay, so it's essentially a consistent, isolated little sandbox for your code, ensuring a predictable execution context every single time it runs.
Precisely. This setup ensures that your code runs in a predictable, consistent, and isolated environment, regardless of the underlying physical hardware or other functions that might be running on the same host machine managed by AWS. This level of abstraction significantly simplifies the developer experience by removing concerns about the underlying infrastructure details, allowing you, again, to focus purely on your application logic.
That clarifies the inner workings beautifully. But Lambda isn't just about the basics, right? It has a wealth of advanced capabilities that really differentiate it and solve common developable pain points. Let's explore some of the key features that make it so powerful, starting with how you configure, control, and deploy secure applications effectively.
Indeed. And these features often evolve quite rapidly, too. One of the simplest yet most profoundly impactful features for managing configuration are environment variables. These allow you to modify your application's behavior, things like database connection strings, external API keys, feature flags without requiring a new code deployment.
Well, that's huge.
It really is. Imagine needing to change a setting for a test environment versus production. You can just update an environment variable directly through the Lambda console, the CLI, or, ideally, via your infrastructure as code tool. All subsequent invocations of your function will immediately pick up that new value without you having to rebuild and redeploy your code package. This is incredibly valuable for managing different configurations across development, testing, and production environments, or for doing things like gradual feature rollouts.
That's a huge time saver and significantly reduces deployment risk, especially for critical production systems. What about managing different versions of your code itself? Especially when you're introducing new features or making iterative improvements, how do you handle that safely?
That's elegantly handled by versions. Lambda allows you to create immutable versions of your functions.
Immutable meaning unchanging.
Exactly.
Yeah.
Every time you publish a new version of your code, it gets a unique version number or identifier, and the previous versions remain available and runnable. They aren't overwritten. This is absolutely critical for safely testing new features in isolation while maintaining stable production environments. You can even use features like aliases to point to specific versions, and then route a percentage of your live traffic to a new version for A/B testing or conduct canary deployments for gradual rollouts.
Canary deployments, like the canary in the coal mine. Test it small first.
Precisely. Test it with a small percentage of traffic. If everything looks good, gradually increase the traffic. If an issue is detected, you can instantly roll back to a known stable version by just pointing the alias back. It provides really robust control over your deployment pipeline and significantly reduces risk.
And if you have a growing number of functions, which often share common code or dependencies, maybe helper utilities or specific libraries, how do you avoid the classic problem of code duplication and the maintenance nightmare that comes with it? Copy-pasting code across multiple functions seems incredibly inefficient and error-prone.
Oh, absolutely. That's exactly where Lambda layers come in as a really powerful solution. They optimize code reuse and maintenance by allowing you to share common components across multiple Lambda functions. Think of it like a shared library. Maybe you have a set of custom utility functions, or specific third-party dependencies, or even custom runtimes that many of your Lambda functions need.
Right, things everyone uses.
Instead of bundling that code or those libraries into every simple function deployment package, which bloats their size and slows deployments, you package them once into a layer. Your functions then simply reference that layer. This significantly reduces the size of your individual function deployment packages, speeds up deployments, and dramatically simplifies maintenance because you only need to update the shared code in one place, the layer.
That's a very smart way to modularize your serverless applications, ensuring consistency and efficiency. And for ensuring the integrity of your deployment pipeline, especially in regulated environments, how do you guarantee that only trusted approved code makes it into your production environment?
For that crucial security control, you have code signing for AWS Lambda. This feature allows you to enforce security compliance by ensuring that only approved code, meaning code that has been cryptographically signed by a trusted authority using AWS Signer and then verified by Lambda at deployment time, reaches your production systems.
So it checks the signature before deploying.
Exactly. It's a critical layer of trust and integrity for your deployment pipeline. It helps prevent unauthorized or malicious code from being deployed, which is paramount in regulated industries like finance or healthcare, or just for any sensitive application where code integrity is non-negotiable.
So those features really help with the configuration, modularization, and deployment side of things. Now let's talk about performance and reliability, especially when dealing with those notoriously unpredictable traffic patterns that can suddenly hit your application. What controls do you have there to maintain responsiveness and manage costs?
This is a really important area. One of the most critical aspects for managing performance and cost is understanding and using concurrency and scaling controls. These allow you to precisely manage your application's responsiveness and resource utilization, particularly during those unpredictable traffic spikes.
How so? What kind of controls?
Well, you can define how many concurrent instances of your function can run at any given time. There's reserved concurrency, which guarantees a certain number of invocations exclusively for a critical function. This prevents other, maybe less critical functions in your account from consuming all available concurrency and starving your important one.
Okay, so you guarantee resources for important stuff.
Right. And conversely, there's provisioned concurrency. This allows you to pre-initialize a specified number of execution environments ahead of time and keep them warm, ready to respond instantly.
Addressing the cold start problem.
Exactly. It virtually eliminates cold starts for predictable high traffic periods or for latency-sensitive applications, ensuring consistent low latency when it matters most, like for interactive APIs. This gives you really fine-grained control over your function's behavior and performance under various loads.
Okay, you mentioned cold starts. That's been one of the long-standing challenges, or at least a perceived limitation, with serverless, right? That initial delay when a function is invoked for the very first time or after a period of inactivity as the whole execution environment spins up. Has Lambda effectively addressed that more broadly now?
Yes, significantly, with a feature called Lambda Snap Start. This feature, initially for Java functions but potentially expanding, is an absolute game changer for latency-sensitive applications. Lambda Snap Start dramatically reduces cold start times, often providing sub-second startup performance.
Sub-second? How?
It works by taking a snapshot of an already initialized execution environment after your function's initialization code is run. Then, when new invocations come in, Lambda resumes new environments from that cached snapshot, bypassing most of the lengthy initialization process.
Wow, that's clever.
It really is. The truly revolutionary insight here is that it makes Lambda viable for a whole host of use cases previously relegated to persistent containers or virtual machines due to latency concerns. It effectively expands Lambda's domain significantly, making serverless a truly competitive choice for almost any interactive workload where low latency is paramount.
And does it require big code changes?
That's the best part. It typically requires no changes to your existing function code. You just enable it via configuration.
That's incredibly impactful for real-world applications where every millisecond matters for user experience. Okay, what about handling large amounts of data coming out of a function? Sometimes a function's response can be quite substantial, like generating a big report or streaming media.
For that specific scenario, you now have response streaming. This feature significantly optimizes function performance by allowing your function to deliver large payloads incrementally back to the client.
Incrementally, so not all at once.
Exactly. Instead of waiting for the entire response to be generated and buffered in memory before sending it back, your function can start streaming parts of the response as they become available. This is particularly beneficial for applications generating large reports, maybe processing large media files or dealing with extensive API responses. It dramatically improves the perceived user experience because the application feels faster. Data starts arriving much sooner, even if the total generation time is the same.
Right, the user sees something happening sooner.
Precisely. Reduces that feeling of just waiting.
And for developers who are already deeply ingrained in the container ecosystem, perhaps they've built workflows around Docker or Kubernetes. How does Lambda cater to them? Does it force a complete re-architecture away from containers?
Not at all anymore. Lambda now fully supports container images as a deployment package type, alongside the traditional ZIP archives. This means you can package your Lambda functions especially those with complex dependencies, custom runtimes, or maybe just a larger overall footprint, using standard container workflows and tooling like Docker that you're already familiar with.
So I can Docker build my Lambda function.
Essentially, yes. You build a container image based on AWS-provided base images, or even your own custom Linux-based images, push it to Amazon ECR, Elastic Container Registry, and then deploy your Lambda function from that image. This provides much greater flexibility and consistency for developers accustomed to containerized environments. It allows our function packages up to 10 GLBs in size, which is much larger than the ZIP limits, and enables the use of almost any custom runtime or dependency that can run on Amazon Linux too.
That really lowers the barrier to entry then.
It really bridges the gap for teams already using containers, providing a familiar path to serverless adoption without forcing a complete paradigm shift in tooling.
It's clear they're making it easier for a wider range of developers and workflows to embrace serverless. Finally, let's talk about connecting Lambda functions to other services and integrating them seamlessly within a broader cloud architecture. What are the key features for that connectivity and integration piece?
Integration is absolutely key, you're right. No function is an island. First, for security and internal access, a crucial feature is VPC networks integration. This allows your Lambda functions to securely access resources within your private network, your virtual private cloud, or VPC. Things like databases running on EC2 or RDS, internal APIs, caching layers like Elasticache, or maybe legacy services that aren't, and shouldn't be, exposed to the public internet.
So Lambda can talk to my private stuff securely.
Exactly. This is crucial for securing sensitive resources and enabling hybrid cloud architectures where some resources remain in your private network.
That's a common and critical requirement for enterprise applications, ensuring data never traverses the public internet unnecessarily.
Okay, and what about managing state or sharing persistent data across different function invocations? That's historically been a challenge with inherently stateless, serverless functions, hasn't it?
It has been a common challenge, yes. That's where file system integration comes in as a significant capability. This feature allows your Lambda functions to mount and access an Amazon EFS, Elastic File System volume, directly within the execution environment.
EFS, that's like a shared network drive in the cloud.
Essentially, yes. A scalable, shared file system. This means your functions can share persistent data and manage stateful operations across different invocations, even across concurrently running instances. For example, your functions could access large shared datasets, perhaps machine learning models that are too big to fit in the function's deployment package or memory, or shared configuration files that need to be updated centrally.
And that's a big deal. It elegantly addresses a historical challenge in serverless, providing a performant, scalable way to manage shared state or large data sets that are too big for a function's ephemeral storage or memory across what are otherwise ephemeral function executions.
Okay, that's a big deal for certain types of applications that rely on shared storage. Now, sometimes you just need a simple HTTP endpoint for your function, maybe for a webhook integration or a very straightforward internal API. Is there an easy way to do that without setting up a whole API gateway instance with all its, bells and whistles?
Yes, there is, and it significantly simplifies certain use cases. It's called function URLs. Function URLs allow you to create public-facing HTTP or HTTPS APIs and endpoints directly for your Lambda function without requiring any additional services like Amazon API Gateway.
Just point a URL at the function.
Pretty much. You enable it with a click or configuration setting, and AWS gives you a unique HTTPS endpoint that invokes your function directly. You can secure it with IAM authentication or leave it open for public access if needed. For simpler use cases, such as receiving webhooks from third-party services, building basic public APIs, or creating simple custom integrations, this greatly streamlines the process of exposing a Lambda function directly to the internet. It makes it incredibly straightforward and fast to get started when the full power and complexity of API Gateway isn't really needed.
That sounds incredibly useful for quick integrations. And finally, what if you want to add external monitoring, security tools, or even custom operational hooks directly into your Lambda environment, but without modifying your core function code itself?
That's where Lambda extensions come into play as a really powerful augmentation mechanism. Extensions allow you to augment your functions with monitoring, security, governance, and operational tools from third-party vendors. Think observability platforms like Datadog, New Relic, Dynatrace, security agents, or even your own custom tools.
How do they work? Do they run separately?
They run within the Lambda execution environment, alongside your function code, but in their own process. They can hook into the Lambda lifecycle before and after invocation during shutdown. This provides a powerful way to integrate additional capabilities directly into the Lambda lifecycle without adding any code or dependencies to your core function logic. It means you can bring your preferred observability, security, or governance tools right to where your code runs, centralizing visibility and control without cluttering your business logic. It really enhances the overall operational posture of your serverless applications.
Wow, those advanced features truly make Lambda an incredibly versatile, powerful, and increasingly mature platform for a vast array of use cases. It's come a long way. But as with any sophisticated technology, particularly in a cloud environment, there are always practical considerations and potential pitfalls that users might encounter. Let's shift gears slightly and talk about how to interact with the Lambda API effectively and some common challenges, maybe some gotchas, that can arise.
Yes, this is a crucial section for anyone seriously building with Lambda, especially for avoiding frustrating technical snags and ensuring smooth operations day to day. When you're interacting with the AWS Lambda API, whether it's to deploy new functions, configure settings like environment variables or concurrency, retrieve logs, or manage those event source mappings we talked about, the highly recommended and by far the easiest path is to use one of the AWS software development kits, or SDKs, for your chosen programming language.
Okay, so if I'm a Python developer, I'd rely on the Boto 3 SDK. If I'm using Node.js, the AWS SDK for JavaScript, Java has its own, Go has its own, and so on. Is that correct?
Exactly. And the reason this is so strongly recommended is that the SDKs handle a tremendous amount of crucial complexity automatically, abstracting it away from you, the developer. They take care of fundamental tasks like request authentication, specifically using something called AWS Signature version 4, which is a complex cryptographic signing process needed to securely authenticate your API calls.
Right, that sounds complicated.
It is. The SDKs also handle the serialization and deserialization of data correctly and provide robust management of the underlying network connections, including things like automatic retries for transient errors and proper error handling. It saves you a phenomenal amount of development effort and significantly reduces the surface area for subtle, hard-to-debug errors. That lets you focus on what you want to do with the API, not how to painstakingly construct the perfect HTTP request to talk to it.
Okay, but what if someone, for whatever reason, decides not to use an SDK? Maybe they're in a language without official SDK support or they have some other constraint. What's the alternative and why is it so much more complicated or error-prone?
Well, if you choose not to use an AWS SDK, then you are essentially on your own for handling that entire communication layer with the AWS API endpoint. This means you'll need to manually authenticate every single request by generating and providing a valid signature version 4.
And that's the hard part.
That's the really hard part. It isn't trivial at all. It involves a complex, multi-step cryptographic signing process. You have to correctly canonicalize the request, hash various parts of it using specific algorithms, sign it with your temporary AWS credentials, and incorporate elements like the request date, region, and service name precisely. While technically possible the specification is documented, it's significantly more prone to subtle implementation errors that can be incredibly frustrating to debug. It's also much more time-consuming to implement correctly and securely, and requires a deep understanding of the AWS authentication protocols.
Okay, message received.
Yeah.
Use the SDKs.
Pretty much. This is precisely why the SDKs are the overwhelmingly recommended path. They bake in all these best practices and simplify development significantly. Avoid the pain if you can.
Now, you mentioned a very common and often perplexing pitfall certificate errors when trying to connect to AWS services, including Lambda. What causes these and what's the typical solution? Because for many developers, this can be a real head-scratcher that pops up unexpectedly.
Yes, this one catches people out quite often. What's often overlooked and can indeed cause frustrating certificate validation errors when using an SDK or even just your browser trying to access the AWS console is the interaction between the SSL/TLS certificates on the AWS servers and the certificate authority, or CA, certificates stored on your local computer.
My computer. How does that affect connecting to AWS?
Well, the problem typically occurs when AWS updates the certificates on their servers, which they do periodically for security, and those new certificates are signed by a newer or different CA that isn't recognized by the potentially outdated CA certificates in your computer's trusted root store.
Ah, so my computer doesn't trust the new AWS certificate.
Exactly. The root cause is that the AWS SDKs, and your web browser for that matter, rely on the CA certificates that are installed and trusted on your operating system to validate the authenticity of the server they're connecting to. So, if your computer's trust store is outdated and doesn't contain the root CA certificate that ultimately signed the AWS server certificate, your SDK or browser will fail the connection. because it cannot establish a trusted, secure TLS connection. You'll get that dreaded certificate error.
Okay, so the simplest and most proactive solution sounds like just keeping your own machine, whether it's your development laptop or maybe a CI/CD build server, consistently up to date.
That's precisely it. The most straightforward and universally applicable solution is simply to keep your computer's operating system and its bundled CA certificates up to date. Regular OS updates, Windows Update, Mac OS updates, Linux package updates typically include updated CA trust lists. These updates usually resolve these issues automatically by ensuring your system recognizes the latest trusted root CAs used by AWS and other secure websites.
But what if you're in, say, a big corporate environment?
That's a good point. If you encounter this in a corporate setting, where you might not have administrative privileges or directly manage your own computer's updates, you might need to engage your IT administrator. They may need to assist with the OS update process, or perhaps manually install the necessary root certificate bundles onto your machine or the affected servers.
Are there specific minimum versions of operating systems or Java environments, or perhaps particular certificate authorities that people should be aware of, just in case they're troubleshooting in a more constrained or maybe a legacy environment?
Yes. The source material actually provides some helpful specifics that can guide troubleshooting in those trickier situations. For Microsoft Windows, generally you need updates from January 2005 or later to include the necessary roots. For Mac OS X, versions 10.4 with a specific Java update from Feb 2007, or Mac OS X 10.5 from October 2007, and all later versions contain the necessary CAs. If you're on Linux, specifically Red Hat Enterprise Linux 5 from March 2007, 6, and 7, and their derivatives like CentOS 5, 6, and 7, they all typically include at least one of the required CAs in their default trusted certificate stores.
Okay, that's useful context for older systems. And for Java, which is obviously a widely used language for AWS development, are there particular versions that are known to include these necessary certificates? Because Java manages its own trust store sometimes, right?
Right, Java can have its own Casserts trust store. For Java versions 1.4.212, dating back to May 2006, 5, Update 2, March 2005, and importantly, all later versions, including Java 6, December 2006, 7 and 8, and beyond, contain at least one of the required CAs in their default trusted lists. This is a crucial detail for developers using these specific runtimes, as running on an older, unpatched Java version could potentially lead to these connectivity problems.
Good to know. And what are these specific CAs that are actually required for accessing the Lambda Management Console or the API endpoints? It sounds like there's a specific set of trusted authorities AWS relies on.
Yeah, your client machines, your laptop, your server, whatever is making the connection, need to support any of the following certificate authorities: Amazon Root CA1, Starfield Services Root Certificate Authority G2, or the older Starfield Class 2 Certification Authority. While the root certificates from the first two authorities, Amazon and Starfield G2, are available directly from Amazon Trust Services for manual download and installation if you absolutely need to do that. Again, the documentation strongly implies that simply keeping your operating system and your Java runtime updated is the more straightforward and generally applicable solution for most users.
Right. Let the OS updates handle it if possible.
Exactly. This whole section is really crucial for practical implementation, helping you troubleshoot and prevent those common frustrating connectivity issues. It really highlights that even in a serverless world, where you don't manage the server itself, client-side hygiene like keeping your own operating system and certificates updated remains vitally important for smooth and secure operations.
So even when you're abstracting away the server, the connection to the service still matters profoundly. It's that last mile, or maybe the first mile from the client, that can trip you up if you're not careful.
Precisely. You still need that secure handshake.
And just like that, we've journeyed through the incredibly fascinating and, I think, truly transformative world of AWS Lambda. We began by shedding that common headache of server management, diving deep into the core concept of serverless, and understanding how Lambda ingeniously abstracts away all that infrastructure complexity, leaving you responsible for basically just your code.
We then explored the why, really understanding when and where Lambda shines brightest. We saw its immense power in real-time stream processing, its effortless scalability for web and mobile applications, its utility for file transformations, database integrations, and even handling routine scheduled tasks. It's clear how adaptable it is, fitting into a multitude of use cases, always with that core promise of automatic scaling and usually unparalleled cost efficiency.
We peeled back the layers on the how, deconstructing its fundamental event-driven model, understanding the critical role of security permissions using IAM, and glimpsing inside those consistent execution environments that give your code a reliable, isolated home. And then we truly dove deep into its advanced capabilities, exploring everything from flexible environment variables and robust versioning for safe deployments, to efficiency-boosting Lambda layers for code reuse, critical code signing for security, performance-enhancing snap start for tackling cold starts, and the sheer versatility offered by container image support and file system integration for stateful workloads.
And finally, we covered those crucial practical considerations, emphasizing the immense importance of using the AWS SDKs for seamless interactions with the Lambda API and demystifying those pesky certificate errors that can sometimes crop up unexpectedly. It's a good reminder that client-side vigilance and system hygiene are still absolutely key, even in a serverless paradigm. You can't ignore your own machine.
This deep dive has truly illuminated how Lambda empowers developers and businesses to innovate faster, scale effortlessly, and dramatically reduce operational overhead by abstracting away those nagging, time-consuming infrastructure concerns. It genuinely frees up incredible amounts of time and resources for what truly matters,
Yeah.
building revolutionary applications and focusing squarely on business value.
It really shifts the focus. So, considering how deeply AWS Lambda integrates into nearly every aspect of modern cloud computing, from processing real-time data streams to powering mobile apps, running intricate back-end workflows, and even executing scheduled maintenance tasks, here's a final thought for you, our listeners. What's one area of your own work, or perhaps just a personal curiosity, a side project maybe, that you now see could be fundamentally transformed by thinking in an event-driven, serverless way?
That's a great question.
How might this paradigm shift reshape not just the future of software development as we know it, but maybe even how you approach problem solving in general by allowing you to focus purely on outcomes and logic rather than the underlying infrastructure? It's a truly powerful concept to ponder, isn't it?